In this video, I want to look at how we compose the symmetries of the equilateral triangle, because each symmetry can be thought of as a function, and so what we really are doing is function composition. So here are our 6 symmetries of the triangle, and what I want to do is I want to state what I want to try and find in English, and then once I have that, we'll work on using these pictures to figure it out. So let's start with this idea. Suppose I want to first do rotation rho 2 and then do reflection mu3. Now, if I want to write this mathematically, this is a function composition, and function composition is written from right to left. So we want to say first do rho 2 and then compose that with mu3. So this is mathematics and this is English. And this is usually called functional notation. And it's not new to you. You have been dealing with this kind of composition for a long time, but you've usually read it as mu3 of rho 2 of x. And what I'm really wanting you to start doing is try and interpret this as first do rho 2 and then do mu3. But now how am I going to actually find this particular thing? Well, I can use the geometry. So I want to think about what the geometry actually is saying. Rho 2 is really a 1/3 rotation in the counterclockwise notation, and mu3 is a reflection across the line of symmetry that runs from the bottom right vertex to the midpoint of the other side. So what I'm going to do is I'm going to start with my triangle, and it is labeled A, B, and C. And I am going to do rho 2. And when I do rho 2, I am going to get the triangle, let's see, A, C, B. A went 1/3 to C, and C went 1/3 to B, and B went 1/3 to A, and that's exactly what that picture up there says. Now I'm going to do mu3 on this triangle. Now I'm actually going to put in my line of symmetry here. The line of symmetry that we're flipping over is this one. And so when we do that, the final answer that we're going to get is going to have A here, and B and C are going to flip-flop. So B is going to be there, and C is down here. So this is the picture of what first do rho 2 and then do mu3 is. But the question is, what is this guy in terms of my symmetries? So I have to go up and I have to look, and I realize this particular picture here, so this particular picture here is exactly this particular picture here. In other words, this answer is the mu2 reflection. The reflection coming back up here, if we denote this one, this is just the reflection across that vertical line of symmetry. And if I put that in originally here, you'll notice that flipping across that red line would get me immediately to here. So what I have in terms of English then is that first do rho 2 and then do mu3 is going to be equal to mu2. Now, we have this other notation that we can look at as well, and I want to see if I can somehow use it to shortcut drawing all of these pictures. It's important to realize that drawing the pictures can get us where we want to go. But we also have these other notations. So what I now want to do is I want to focus in on looking at this way of denoting row 2 and this way of denoting mu 3 and see if I can use them to come up with a way of figuring out that the answer should be mu 2 without drawing all of the triangles. So let's write down those two things. So row 2 is top row ABC, bottom row CAB. And mu 3 is top row ABC, bottom row BAC. Now, if I'm wanting to first do row 2 and then do mu 3, I'm going to want to write this as first do row 2, then do mu 3. So you'll notice that mu 3 is here and row 2 is there, and we are suppressing the composition, although if you want to, you can stick it in. Now I am going to be thinking in terms of how do I figure this composition out. It is important to realize this is not matrix multiplication. I'm going to do what I call a tracing algorithm. We're going to start here at A. Row 2 sends A to C, and then mu 3 sends C to C. So the composition sends A to C. And just to make it clear, A goes to C and C goes to A, so A goes to C. Well, let's see, what about B? B goes to, let's put this in a different color. B goes to A, and then A goes to B. So B goes to A, and A goes to B. That means B stays fixed. And again, just to be thinking in terms of what's going on here, this column gets followed by that column. In other words, B goes to A and A goes to B, so B goes to B. Our final column is going to look like this. C goes to B, and then B goes to A. So C is going to go to A. And if we notice that this particular thing is exactly the two-row notation for mu 2. This is how we can quickly compute permutation products. And when you are trying to verify the rest of the table that the author gives for the composition table for D3, you can either draw triangles or you can do this tracing algorithm to compute the composition. The final thing that I want to note is a notation convention in abstract algebra. So there is an important notation convention in abstract algebra. In abstract algebra, we are never going to be multiplying functions together. And so if we have f and g are functions, then if I write something that looks like fg, that means first do g, then do f. In other words, in abstract algebra, this particular set of symbols means f of g. It is the composition of f and g. This is not true. So this notational convention is not true in other areas of mathematics. In particular, if you are enrolled in a course like real analysis or complex variables or some of the other upper division courses that we offer in the department, and you see this inside of a calculus class or a real analysis class, this is going to be f of x times g of x in most math classes. But this means f of g, which if we have the argument is f of g of x in abstract algebra. And that is a really important notation convention to get down in your notes and get used to seeing. And with that, I'll end this video.